Hello everyone, my name is Connor Smiley, and in this video I'm going to show off an AStar pathfinding visualizer I made. I've made a couple AStar related videos on my channels before, but this is the first one that actually visualizes the algorithm. Now, for brevity's sake, I'm not going to go over how the algorithm works in complete detail, I just want to show off what I've made mainly. So here we go. Currently we can see we've got some GUI to move around our starting tile with this silly little van. So let's keep that at 0, 9. And we've got this end tile marked by the red square. And we can see that currently we're doing 0 iterations for AStar, so this is a pretty wide path, so we're going to need multiple iterations for this to work, and we've got a couple render states as well, so number 3 displays the most information, so let's go through it iteration by iteration. So AStar, as you know, searches all nearby tiles, and it's basically a combination of Dijkstra's algorithm coupled with greedy first search. So it's gonna attempt to choose the tile with the lowest score and keep choosing the tile with the lowest score until it encounters problems, and then it's gonna backtrack. So we can see here iteration 1, 2, 3. I've got a bit of a heat map, so it looks like we're pathing directly towards the target right now. So we start with 11, 9, 8, 7. I've added some different costs to each tile, so these darker gray tiles have a additional cost of 100, whereas these gray tiles have no cost, and whereas about to see these blue tiles will have a cost as well, so we'll see AStar in action. So here we're still just going straight towards our target along the diagonal, but now when we search around these blue tiles, we can see they've got a cost of 50, so coupling that with our distance heuristic, this is now the suboptimal path, so we're going to backtrack and AStar is going to resume its search at either of these tiles scored with a value of 6. So it looks like we go left first. We discover 6.8, which is still the lowest score so far. So we're going to keep going. Or no, sorry, 6 was the lowest score so far. So we keep going. We're tied. So we discover 7. So we're going to search this 6.8. We get 7. So we're going to search the ends once more. Looks all right, so we get 7.4, so that's why we searched the 8. So now we should be able to search the edges, and sure enough, we're making some progress. And yeah, it looks like this is going to take us on the optimal path, or at least optimal as far as AStar is concerned. So there we go, we keep going, we're unobstructed, and once there's a valid path to the destination, we're going to use some janky linear interpolation to move our van along this beautiful rainbow path. And notice how it goes diagonally because my algorithm is using Euclidean distance, contrary to Manhattan distance, and it's searching diagonals rather than left, right, up, down, but it can be tweaked to use Manhattan as well as ignoring diagonals. So let's pull back the curtain on that and check it out. And also we can see that the path will change if we move the end down here. So it's just gonna go on the bottom instead of the top because that's a touch more optimal. Again, just to be clear, AStar is not an optimal pathfinding algorithm, it's an efficient pathfinding algorithm because we can see due to greedy first search, it's going to path brute force towards the destination, and if it encounters some issues, then that's going to make the path suboptimal. So something like Dijkstra's will search basically every tile and it's borderline guaranteed to have an optimal path, but AStar reduces that precious CPU time. Anyways, I can change my render state to just show the complete path, so I probably should have changed that a while back. And I can also just remove those numbers by doing that, so this one's not too useful for educational purposes, but nice to see. And yeah, let's take a look at some of this code. So again, not going to be explaining the algorithm in great detail, just showing off key code components. So we might see more of this overarching framework in future videos, but I basically use the DirectX toolkit for rendering because I didn't want to spend half my life wrangling graphics code just to make simple 2.5D demos. So We've got a 2D array that's our tile map, just a bunch of integers that map to different tile values in the world based on their array positions. We've got a path, which is a vector of cells, which I'll explain in a moment, start and end tiles, some integers to help with the linear interpolation, and I also need to store this vector of tile nodes to have my tile scores visualized. And these are just some lifecycle callbacks in my engine. For the scene, again, lerp is normally a math function, so it's implemented for vector 2, 3, 4, and I had to make another implementation just for cells, since this is the only scene that uses cells, but it just does textbook lerp. And it also, so it'll work in cell coordinates and return a position and direction in world space. Some code to handle GUI inputs using mgui. This is just setting up my 2.5D perspective because we're in 3D, so we simplify that with an orthographic projection with an appropriate lookat matrix. I should zoom this in a bit. And then an update function that just handles the linear interpolation. And lastly, my rendering function that calls into different rendering functions depending on that render state value. And you can see I'm being really lazy here and not using enums, just 1, 2, and 3, because this is just my code and we're not trying to impress people with world-class programming techniques. But I'll stop rambling. Here we go. So there's two classes behind the scene. We have tile map, which again just takes these values here and maps them to something more human readable. So I called this a tile type that can be interpreted as an integer. So we saw rock has values of 100, water has 50, etc. I don't think I used grass in this demo. And I've got a couple data structures, node and cell, so we'll get into node later, but cell is just using some type safety so that I can work in tile coordinates, which are basically 2D array coordinates rather than screen coordinates, just for added safety and clarity. And we can compare tiles, just checking if row and column are equal, as well as comparing nodes, which will compare their score as well as their tile positions, I believe. There's the two heuristics, so just absolute value versus Pythagorean theorem. Little type def right here just to simplify tile map creation and giving it a fixed size so we can use array for compile time static memory. Not that it matters at a demo of this size, but yeah. Helper function for returning a vector of surrounding tiles given an input tile within the tile map, a function to conveniently flatten a 2D array position. So again, an X and Y cell structure will return an integer, a few rendering functions. So this renders the entire tile map, and then given a type and an index, we can render the tile according to its type. So, rock is dark gray, water is blue, etc. Some quantization and localization are the fancy words from converting between tile and screen coordinates and vice versa. And then we've got our node, which is going to make more sense when I show off the actual AStar algorithm. It basically needs everything wrong with C++ to function so that I can use some powerful STL data structures that require a bunch of default constructors and custom constructors. And yeah, but basically all this does is it stores a cell that came before it, so we can create a linked list by working backwards from destination to start once we've reached the end to build a valid path. And it calculates its f-score, which is the distance score versus heuristic, so I called it cost in my case. And yeah, I really should have just showed the CPP file, but yeah, we can see right here is the neighbors function. So originally I had this as a for loop, but that was causing some problems because you can see some bounds checks right here, ensuring that we get valid array indices. So for example, if the first tile we checked was off screen, that would cause the for loop to exit early, returning an incorrect amount of neighboring tiles. And then here, this not super important, just uses my simple primitive rendering that internally uses DirectX Toolkit rendering, the math for quantization and localization, color tiles based on type, add costs. So again, rocks are expensive, followed by water, grass, air. And yeah, here, this was responsible for the heat map. So just a user defined static array of different colors. And tiles would be rendered with their heat map based off their F score. So let's get into the actual AStar implementation. We can see that just a vector of tiles are returned because I didn't want to work in world coordinates, because that should be up to the path following mechanism, which should be independent of the path finding mechanism. So this algorithm would be more appropriate for an actual solution, whereas this is the visualized one because it outputs the array of tile nodes that are calculated, as well as a certain amount of iterations to attempt, because you saw with my slider I would increase or decrease the iteration. But yeah, let's look at the find path debug implementation. Actually, let's just look at find path because they're the same thing. This one's just a bit simpler because there's no added debug code. So yeah, given a start, an end, and a map, find the path from start to end, if any. And a couple optimizations here. So I'm using a 1D array mainly for convenience, so I can flatten it and I don't need to keep track of a 2D position. And I'm pre-allocating stuff equal to the amount of tiles in my map for the absolute worst case, as well as it's also just cheaper than dynamically growing that every time we have to append a new tile. And this is the real beauty of this algorithm, using this templated priority queue. So since nodes have a comparison function, we can order our nodes and consume them based on which ones have the lowest F score, which is going to allow our AStar algorithm to do greedy first search by evaluating the node with the lowest score first. So by default, we push the starting tile onto our unexplored list, and we go until there's no tiles to explore or we found a path, so we consume the lowest tile. We test if we've reached the end. Otherwise, we make sure we do not check it again. Then we're gonna search the corresponding tiles and try and find out if there's a better scoring tile to continue our search on, so we can see our distance heuristic as well as our cost heuristic, which is the completely arbitrary part of AStar. And yeah, this is just appending a better value if we can find one. And by the time that's over, we should find a path. I got a little lazy by ensuring based on my tile grid that you're always guaranteed to have a valid path. So at this point, we just walk backwards through our array of paths and we build it using the linked list, because we remember that given this node structure, nodes also store their parent cell, so we can just reverse that list and we are left with a nice little array of tiles. So yeah, thanks for checking that out. That's my AStar Visualizer. One thing I'd like to do in the future is I've basically used more or less the exact same AStar algorithm in multiple tech demos at this point, so I don't think I need to touch this algorithm anytime soon, but it would be cool if I made some sort of pathfinding interface so I could just overload a few functions or maybe make this more templated. Although generally every time I make this algorithm, it requires a little bit of tweaking to handle different world coordinates or different tile map representations, but some food for thought. All right, goodbye for real.